All right, hello again. This is Jeff Scott. Once again, I'm coming at you with some of the lectures regarding the Microsoft Security Development Lifecycle. And I am now going to go over cross-site scripting. This is kind of a long presentation. The good news is the next two that are going to come are about the same length combined as this one is. So we'll talk about what cross-site scripting, typically referred to as XSS, what it is, how it is, the major players involved, different types of cross-site scripting attacks, and how to prevent cross-site scripting attacks. So, as mentioned here, cross-site scripting is a code injection attack. All right, as it says, it allows an attacker to execute malicious JavaScript in another user's browser. So for that reason, as mentioned on here, the attacker doesn't target the victim. In other words, what they're doing is they're exploiting a vulnerability in the website. They're adding code to a website because they want to get the user to be able to execute that code. And again, the victim is unaware that there's any malicious JavaScript. In reality, the website is unaware. All right, as it says there, the website has just acted as an unintentional player or accomplice to the attacker. The only way that this works is to inject malicious JavaScript code into one of the pages that the victim downloads from a site. You know, as it says, this can happen if the user directly includes user input in pages, so typically in things like forms. And this is kind of a high-level overview picture here of how it works. So what we're talking about here is, again, the hacker comes in and infects the web page with malicious JavaScript. The victim unknowingly comes in and visits the web page. So the victim's machine gets injected, all right, with that malicious JavaScript. And what we have here is doing something bad. Well, quite often what this can involve is something like grabbing information from a user's machine, even something, something as valuable as session cookies or something, where the attacker can, for all intents and purposes, become the user. And as mentioned here, it might seem trivial because JavaScript has got the reputation for, well, you can't do that much with it anyway. It's a client-side tool. It runs in a safe environment, etc. But JavaScript has access, as mentioned there, to cookies. JavaScript can be sent HTTP content requests. This XML HTTP request is kind of what funnels or drives AJAX, which is asynchronous JavaScript in XML, the way that you do partial page refreshes. So it is literally used all over the web. As mentioned there, to transfer data between a client and a server. JavaScript can also make modifications to the HTML via the DOM or document object model to, again, add things onto a web page, remove things, or modify things that are on a web page. Well, three things that this can lead to. The first is cookie theft. I already mentioned this. The attacker can access the victim's browser cookies and have those cookies sent to their own server. And there might be things in there by themselves. Cookies aren't dangerous, but cookies can contain any kind of information. For instance, it wouldn't be impossible to have cookies contain password information, credit card information, login information, whatever it happens to be. Keylogging can also be done. Keylogging probably isn't as major a thing today as it was years ago, but with keylogging, what happens is the attacker can watch as the user can basically record every keystroke the user is making. And the reason that that's important is if they can do that, then as they log in or as they go to different sites or as they put their credit card or other personal PII, personal information into the system, they can grab those keystrokes and send them to their own server. There's also phishing attacks, where as it says, you can insert a fake login form. We've all seen these. Some of them are just so absurdly, out there that you'd never consider them. Hi, name my is president, king of some country. Need $20,000, will pay back $2 million 2 weeks now from, type of thing. Well, who's going to fall for something like that? But what it takes is if you have somebody click on something that looks realistic, click here to answer our survey and be put in for a chance to win $1,000 type of thing. As mentioned there, all of these different attacks have something in common. The script that has been injected maliciously by the attacker is now considered a legitimate part of the website. You know, the website is just code. It has no way of knowing whether or not the information that's in it is valid or invalid, so to speak. So the bottom line, as it says, what this does is it compromises. It compromises the website, it compromises the user, it compromises the user's machine. All right. So when you start to talk about the different actors, so to speak, who are involved in cross-site scripting attack, as mentioned there are three of them. The first, as mentioned, is kind of the innocuous website. It serves up the HTML pages. All right. It typically has a database that stores the input from the site's pages. And again, typically this is an innocent player when we're talking about a cross-site scripting attack. Then you've got the victim, another innocent player. They're a quote, normal user, unquote, of the website. So as mentioned there, they innocently request pages from the website via their browser. Then you've got the attacker, who intends to launch some kind of a cross-site scripting attack on the victim. They also have a server at their disposal. Remember, all the server has to be is just a computer. All right? And the attacker wants to use their server to steal information that they consider valuable from the victim. There are three basic types of cross-site scripting attacks. All right? The first is a persistent cross-site scripting attack where the malicious string originates from the user's database. The next is a reflected cross-site scripting attack where the malicious string originates from the victim's request, so from the database, from the victim. And the third is a DOM-based cross-site scripting attack where the vulnerability lies in the client-side code and not in the server-side code. So with a persistent, or also known as a stored cross-site scripting attack, as it says, this is what we talked about before. These are the examples that we just were looking at or talking about. As mentioned there, the attacker injects a script, typically referred to as a payload, that is permanently stored. In other words, it persists, so that's where you get the words here, on the target app within a database. So the victim brings up the affected page in the browser, and that payload is then served up as part of the page, meaning the victim is unknowingly going to be executing the malicious JavaScript when he or she views their page. So this is kind of a picture of what happens here. So in step one, the user uses one of the website's forms to insert a malicious string into the database. All right, so that's what we're doing here. Okay. Then in step two, the victim requests a page, all right, from the website. In step three, the website includes the malicious string and sends it, all right, there in response, sends it over to the victim. In step four, the victim's browser executes the malicious script inside the response. And typically, again, what that'll do is it'll send the user's cookies, all right, it'll send them over to the attacker. And that's the next step. So here, 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 and here. All right. So next, there's a reflected type of cross-site scripting. As mentioned there, the attacker's payload script has to be part of the request sent back to the web server. And as mentioned, must be reflected back so that the HTTP response includes the payload in it. Phishing emails and other social engineering techniques are used to make a victim make a request to the server containing the payload. So what happens is they end up executing the script that gets reflected inside of their browser. It's not a persistent attack, as the attacker needs to deliver the payload separately to each victim. So if we look at this one right here, In step 1, again, the attacker rather is crafting a URL containing a malicious string and sending it to the victim. In step 2, the victim is somehow tricked into requesting the URL from the website. Then in step 3, again, the website includes the malicious string in the response. And in step 4, the browser executes the malicious script inside of the response. So very similar to what we just saw previously. And here are the 4 steps. Finally, you've got a DOM-based cross-site scripting attack. As mentioned here, this is possible when the client-side scripts provide data to the document object model. The data is read from the DOM and outputted to the browser. And as mentioned, if it's incorrectly handled, what can happen is the attacker can inject a payload, and what you can do with the DOM is you can use it to either read information from or write information to the DOM. As it says, the most dangerous part of this is it's often a client-side attack, and the attacker's payload is never sent to the server. That means it's harder for something like a web application firewall to detect it. All right, and it's harder for any security engineer analysis tools to even log it and figure out, because to them an attack has never happened. So in step 1 here, again, the attacker crafts a URL containing the malicious string and sends it to the victim. In step 2, the victim is again tricked by the attacker into requesting the URL. In step 3, the website receives the request, but it does not include the malicious string in the response. In step 4, the browser executes the legitimate part of the response, which causes the malicious script to be inserted into the page. Finally, in step 5, the victim's browser executes the malicious script without them even knowing it. And here are those 5 steps. So the 2 basic things that you have to do in order to prevent cross-site scripting attacks are encoding and validation. Encoding, as mentioned right here, escapes the user input so that the browser interprets it only as data, not as code. And validation filters user input so that the browser interprets it as code without any malicious commands. These things share some stuff in common, such as context. As it says, where secure input handling needs to be performed depends on where in the page the user input is inserted. And I added this little line here, trust no input. Assume that all input is bad. Encoding and validation share inbound and outbound, meaning that secure input handling can be performed either when the website receives input from a user, inbound, or when they're going to insert it into a database, outbound. Encoding and validation share client-server, where secure input handling can be performed on either or both the client side and or the server side. All right. So encoding, as it says there, it involves escaping user input so a browser interprets it only as data and not as code. For example, the use of HTML entities, and I put a hyperlink there, which will convert something like this, like a less than sign, for example. It'll convert it into this, or it'll convert a greater than sign into this. In other words, if someone tries to come into an HTML form and put in a script tag, instead of saying less than sign script greater than sign, it'll say this. The system won't be able to interpret that as being actual code. Encoding has its limitations. It's still possible to get around it and put malicious information in some circumstances. Again, you're trying to mitigate the occurrence of risk. You may not be able to totally get rid of it. All right. As it says, if the goal is to have the user define part of a page's code, well, the user can still do things purposely or unconsciously, let's say. So encoding should be paired with validation. With validation, as mentioned right here, The idea is you're filtering user input so that you remove the malicious input without removing the code associated with it. For instance, you might allow things like M tags and strong tags, but not allow things like script tags. So if somebody wants to bold something in a form, you'd let them do it, but you wouldn't let them inject JavaScript. The way that you typically do this is typically you use either blacklisting or whitelisting. All right? And those are the typical classification strategies, and the typical outcomes of this will be either rejection or sanitization. So, blacklisting, it's hard to do because, as mentioned there, it involves defining forbidden patterns that are not permitted for user inputs. They're complex because finding every pattern and every derivation of every pattern is difficult, if not impossible. And they become stale fast, meaning that new patterns are created and added all the time. All right, the opposite of blacklisting is whitelisting, where you define only allowable patterns, and that's what you allow in and nothing else. The benefit of that is it's more simple, it's easier than blacklisting, and typically it won't become as obsolete as fast as blacklisting. But still, it's problematic because sometimes when what the user is putting in to the system may now seem invalid, where indeed it's valid. So based on the blacklisting or whitelisting, you can reject where the input is simply rejected. That's probably the safest way of doing things, but that may allow things that should be put into the system, it may keep them out. So when you sanitize, as it says, all invalid parts of the input, ideally at least, are then going to be removed, and what's left will be sent. The remaining input will be able to be used normally, and it'll be valid input. So as far as some lines of defense, we've already talked about this. The first line of defense should be encoding. The second line of defense, used along with encoding, should be validation. All right? As mentioned, part of the problems with using this is even a simple lapse in security, something that you forgot to put in. And again, typically, if it would be something you forgot to put in, it would be accidental. You didn't mean to forget to put it in. You just forgot to put it in. So there's a newer line of defense that's known as CSP, or Content Security Policy. As mentioned here, it's a browser-side mechanism that lets the user create some source whitelists for the client-side resources of a web app. So you can use it for such things as not allowing any untrusted sources. So you can have a list of where you would trust information from. No inline resources. So definitely do not evaluate any JavaScript or even CSS where it's possible to put bad payload. And not allow the JavaScript eval command. There are many books that you can read that will say eval is evil. So we've come to the end then. We talked about cross-site scripting and how it's a code injection attack, how it allows the attacker to execute malicious JavaScript in a victim's browser, how it compromises the security of the website and the people using it. We discussed the three major types of cross-site scripting attacks: persistent cross-site scripting, where the malicious input originates from the website's database; reflected cross-site scripting, where the input originates from the victim's request; and DOM-based cross-site scripting, where there's a vulnerability in the client-side code that gets exploited. We talked about the two basic ways to help prevent cross-site scripting, those being encoding and validation. And we also mentioned the newest layer of security that's put in here, which is Content Security Policy. And that's it for this presentation.